Question 1. A. Calculate delta S when 1 mole of liquid water is heated from 0 degree to 100 degree at constant pressure. So constant pressure, entropy change is calculated by NCPM ln T2 over T1. Temperature in Kelvin, 100 degree is 373.15, 0 degree is 273.15, and the answer is 23.49 joule per Kelvin. In B, it asks you to calculate the entropy change for a transformation from solid water 0 degree to gas water 100 degree. So from solid to gas, this involves two phase transition. Let's draw the phase diagram. So water, solid, 0 degree, water, gas phase, 100 degree. Now because entropy is a state function, we can design a path that we can calculate entropy change. So let's assume the solid water phase transition into liquid water at 0 degrees. So constant temperature, constant pressure phase transition. That's delta S1. Alright. And the liquid water heated to 100 degree remains as a liquid. And then 100 degree liquid phase transition to the gas phase. Now delta S2 is liquid heating under constant pressure, and this is the one already calculated. Okay? So this is the heating from 0 degree to 100 degree liquid water. Now delta S1 is the phase transition. The equation is delta H over T. Now in this case, it's fusion entropy and fusion temperature, which is 0 degree. Delta S3 is a similar equation, delta H over T, but it's the vaporization. So here are two phase transitions. Okay, one is fusion, all right? So delta H is 6.0095 kilojoule per mole, and you need to times 1000 becomes joule to calculate the entropy change. Temperature 0 degree, the first phase transition, 0 degree change to 273.15 Kelvin. Okay, the second phase transition, the vaporization entropy change to joule, temperature 100 degree, 373.15 Kelvin. So the total entropy is the sum of the two phase transition plus a constant pressure heating pressure heating entropy change. And that gives you 154.4 joule per Kelvin. So now, what if the question asks you to calculate entropy change not to 100 degree gas phase? Instead, it asks you to calculate entropy to, let's say, water, liquid at 80 degree. How do you calculate? Okay, to calculate that one, let's modify this diagram. Okay. So here we are calculating the entropy change from solid water to liquid at 80 degree. So let's change 80. Okay, so first it's still ice melt into liquid water phase transition. Now it becomes a liquid, so liquid heating to 80-degree liquid. So two steps. Step delta S2. Delta S1 is still the phase transition. Delta S2 is the constant pressure heating NCPM ln T2 over T1. So T2 is 80 degree change to Kelvin. T1 is 0 degree change to Kelvin. So the point is that it's not always 3 steps. Depends on the initial state and final state. Question 2. 1 mole of nitrogen at 20.5 degree 6 bar undergoes a transformation to the state described by 145 degree and 2.75 bar. Calculate delta S. So in this question, the gas changed state from initial to the final. It is helpful to draw a diagram showing how the state changed. So here, temperature goes up and the pressure goes down. And we want to calculate delta S. Remember, entropy is a state function, so we can design a path and we can calculate entropy for each step. So in step 1, the temperature is constant, and we have learned that isothermal compression or expansion, the entropy is calculated by nR ln V2 over V1. Okay, so you can go back to the equation we derived for ideal gas isothermal expansion. It's nR ln V2 over V1. Now, because it's isothermal, it obeys Boyle's law. So if we don't have volume, okay, we can use Boyle's law. V2 P2 equals V1 P1. That means V2 over V1 should equal to P1 P2. And therefore, this equation is nR ln, okay, also P1 P2. Alright, now if we want to write as final over initial, then ln P2 over P1 should be negative of P1 over P2, so negative nR ln P2 over P1. Okay, so that's delta S1. Delta S2 here is constant pressure heating process. So constant pressure heating process should be NCPM ln T2 over T1. Okay, so two adds together, and that's how to calculate. Okay, so let's erase this. So here, this is delta S1, this is delta S2. Okay, one is constant temperature expansion or compression. One is constant pressure heating. And the answer is 17.4 joule per Kelvin. Question 3. 1 mole of an ideal gas with CV, so it should be CVM, equals 3 over 2R, is heated from initial temperature 300 Kelvin and the pressure 1 at 1 bar goes to final temperature 450 Kelvin at a constant external pressure. Calculate Q, W, delta U, delta H, delta S. So at this point, you should be familiar with the calculation of Q, W, delta U, delta H for different processes. This question is about constant external pressure. The W should be calculated by negative external pressure times volume change. Because we don't have the volume we need to calculate. So use ideal gas law. We have temperature, we have pressure, we have number of moles, and also final temperature. Using ideal gas law, we can calculate initial volume, final volume, and then negative external pressure times volume change. That gives you the final results, the work. Okay. Now it's an ideal gas, and therefore delta U should always equals to NCVM delta T. And the delta T is given, initial temperature, final temperature given, so it's easy to calculate delta U. To calculate the Q at this point, we have two ways to do it, because we already have W and delta U. So you can use first law, okay? Q equals delta U. Q equals delta U minus W. That's the first law. You can calculate. That's one way to do it. The other way you can do is, because it's a constant pressure, so the heat is NCPM delta T. And the NCPM can be calculated by CVM plus R. And CVM is given. So you can also calculate, should give you the same result. Okay, so two ways to calculate the Q. To calculate delta H, we know constant pressure entropy is heat. So you can either just let delta H equals Q, or delta H for ideal gas is always NCP and delta T. So again, that gives you the same results. So the only thing new in this chapter is about entropy. So how do you calculate the entropy for constant pressure heating? The equation is NCPM ln T final over T initial. So number of moles, Cp is Cv plus R, CVM plus R. CVM is 3 over 2R plus 1 times R. That's the Cp. Okay, CVM plus R give you Cp. Okay, so next, calculate the surrounding entropy. Surrounding entropy should be the Q surrounding divided by T surrounding. Now Q surrounding is calculated by negative of the Q system. Negative Q system. And so that's why you have a negative 3 over 3.12 times 10 to the third power joule. That gives you surrounding entropy. The total entropy is calculated by the sum of the system and the surrounding. That gives you 1.5 joule per Kelvin. And because the total entropy increase according to the second law, this process should be spontaneous. The last question, calculate the entropy change under standard state condition of 1 bar 298 Kelvin for the following reaction. To calculate reaction entropy, we use the standard entropy of the product minus reactants. So we find the product entropy iron, that's the product, all right, times 3, and water times 4 minus reactants, and 130 times 4. Okay, that gives you negative 308.9 joule per Kelvin. So entropy is negative, entropy change is negative, and that's because you have 4 moles of gas phase in the reactants, but you only have solid liquid in the product. In other words, the system becomes more ordered, the entropy decrease.